Welcome to our presentation, Normalizing Flow as a Flexible Fidelity Objective for Photorealistic Super Resolution. Code and pre-trained models will be available on git.io/AdFlow. Super resolution is an ill-posed problem. As you can see in the figure, one low-resolution image patch can be super resolved to many high-resolution images. This process of adding high frequencies is ill-posed because there are infinitely many solutions for that. The first wave of deep learning uses the L1 loss as the training objective. As you can see in the picture, the super resolutions are still quite blurry. To improve the realism, Ledig et al. Introduced the combination of the adversarial loss and the gun loss. As shown in their illustration, the L1 loss aims to output the average of all plausible super resolution. However, this results in a blurry super resolved image. On the other hand, the gun loss aims to output a natural image. We further illustrate this conflict in that figure. You can see the distribution of natural images that downsample to the same low-resolution image in gray. The output of the super resolution model, when only trained for L1 loss, is in red. Those are the average of natural images that downsample to the same low-resolution image. And in green is the output for a gun loss. The gun loss drags the image to a single output image that resides on the natural image manifold. In this figure, you can see an example for artifacts that are generated for such a loss combination. So how can we reduce this conflict? L1 loss is the negative log likelihood loss of the Laplacian distribution. This can be seen as a one-layer normalizing flow. In this work, we generalize this loss for a more complex distribution. Therefore, we replace the L1 loss with the flow loss. The output of the flow loss is again an image distribution. This distribution is a manifold of the natural images that are downsampled to the same low-resolution image. In the following, we describe the architecture change that results from that. Here you can see the standard architecture when using the SR-GAN approach. The low-resolution image is fed to the generator E, which outputs the super resolution. During training, there are two losses, the adversarial loss and the L1 loss. In the probabilistic view, the L1 loss is computed by calculating the negative log likelihood of the error between those images. In this figure, we show how we generalize the L1 loss to the flow. Therefore, we calculate the negative log likelihood of the forward flow with the ground truth image as input and the encoded low-resolution image as conditional. Further, the output of the model is now coming from the inverted normalizing flow. The negative log likelihood of the high-resolution image given the low-resolution image is calculated using this normalizing flow equation. We decompose it into calculating the probability of Pz, the normalizing flow latent space, and the determinant of the Jacobian. This loss is combined with the adversarial loss. The adversarial loss is minimized with respect to the flow and maximized with respect to the discriminator parameters phi. Here we show a visual comparison of the approaches. While the GAN approach generates artifacts, the AdFlow generates a noisy texture. The combination of both in AdFlow generates a smooth texture and fine details and even regular patterns. Here's a zoom of the books in the library where you can see that even structured information can be generated with it without artifacts. Here are more examples for 6x super resolution. In the paper are more with 8x super resolution. As you can see, especially structured output is handled very well by AdFlow. Our results were verified by a large user study. Here are a subset of them. We compared AdFlow with BaseFlow, which is the same architecture but with neglected discriminator loss. AdFlow versus the popular ESR-GAN, AdFlow versus SRFlow, which has some architectural changes. The code will be available on git.io/AdFlow as well as the trained models.